welcome to integration. So let's begin by deep introduction to integration. Okay, now, so in your logic classes, you heard that integration is nothing but the area under the curve. Okay, now if I give a region, say a rectangle, with the side A into B, then you know what is the area. Its area is nothing but A into B. A into B. So how you get this? Okay, so let's assume that area of unit square is 1 unit square. 1 unit square. With this side 1 unit, it is nothing but a unit square. Its area is 1 unit square. Now let's consider a rectangle with the side A and B, where A comma B belongs to Z. Now divide this A, since it's an integer, divide this A into A equal segment, each of length 1 unit. Similarly, B into B equal segments, and then you will get each as 1 unit. So you divided this a rectangle into A into B equal unit squares. So each unit square has area 1 unit square. Therefore, this rectangle is A into B unit square. Area of this rectangle is A into B unit squares. Now, what happens if A and B? What happens if A comma B are rationals? Say A is equal to P1 by Q1 and B is equal to P2 by Q2, where P1, P2, Q1, Q2 all are integers. Now from this P1 is nothing but A into Q1 and P2 is nothing but B into Q2. Now, using this P1 and P2, let's consider a rectangle with the side P1, P2. See, this is a rectangle with side P1 and this side P2. Since P1 and P2 are integers, area of this rectangle is P1, P2. So, area of rectangle. So its area is equal to P1 into P2. Now divide this P1 into equal segment such that each length is Q1, where Q1 is an again in this length is Q1, this length is Q1, this length is Q1, and so on. And similarly, P2 into equal segment such that each of length is Q2. This is Q2, this length is Q2, this length is Q2, this length is Q2. Draw the lines. So you will get Q1 into Q2 rectangles. You get Q1 into Q2 rectangles. The side Q1 and Q2. Then what is its area? Its area is Q1, Q2. This is by our previous knowledge. Now this rectangle has, okay, wait, this is not sorry, there's a small mistake. Divide this p1 by q1 segment, each of equal length. So there are q1 number of segment, here it is q2 number of segment. I don't know what is the length, what is its length. ಇಲ್ಲಿ ಎಷ್ಟು ಇದರ ಲೆಂತ್ ಏನು ಅಂತ ನಮಗೆ ಗೊತ್ತಿಲ್ಲ. ಆದ್ರೆ ಇದನ್ನು ಎಷ್ಟು ತುಂಡು ಮಾಡಿದೆ, q1 ತುಂಡು ಮಾಡಿದೆ, ಇದನ್ನು q2 ಆಗಿ ತುಂಡು ಮಾಡಿದೆ, q2 times. So I don't know what is this length and what is this. So there are q1 into q2 rectangles. I know only there are q1 into q2 rectangles. Total area is p1 by p2. Then what is the area of the smallest rectangle? That is given by p1 p2 divided by q1 q2. It will be equal to my a into b, because p1 by q1 is a, p2 by q2 is b, it is a into b. Therefore now what is its length? Its length is now p1 by q1, its length is p2 by q2, because idannu nanu q1 times divide madidene, idannu q2 equals divide madidene. So this length is p1 by q1, this length is p2. So if I consider any rectangle, this length is p1 by q1, this length is p2 by q2. Therefore its area is a p1 by q1 into p2 by q2, that is a into b. So that is area of a rectangle with the side rationals is a rational ab, implies area is nothing but a into b. Okay, yes. So moving further, what happens if the sides are rational? So in general, let's consider a rectangle with the side a and b, where a comma b both are real numbers. I don't know whether they are rational or irrational. In such a case, how to find? Using your previous knowledge of real analysis, for every real number there exists a sequence. So for this a, there exists a sequence an, and for b there exists a sequence bn in rationals in Q. That means a and rationals, b and rationals, such that an converges to a and bn converges to b. Now a and bn are rationals. If I consider a rectangle with the side a and bn, then its area is an into bn. We know that if a sequence an converges to a and bn converges to b, then sequence a and bn will converges to a into b. This will give that the rectangle with the side a comma b belongs to R, implies its area is a into b. Now so theory integration is developed around in around 1600 with the great efforts of Leibniz and Newton. Wait a second. Integration is developed in around 1600 with in respect to Newton and Leibniz. Okay, you have to remember that integration is developed much more. You know that you have heard that some are saying integration is nothing but antiderivative, but integration is developed much more before differentiation. Okay, now let's see. So if I have say this is my region, now how to find its area? Okay, let's see. Now divide this region into equal segment in both horizontal and vertical lines. Now, then you will get squares. They assume that all are equal square. It is not visible in my diagram, but assume that all are equal squares. With side, yes. With side, yes. Okay. Now with side, yes. Now mark all the squares which are inside the region. Mark all the squares which are fully inside the region. Okay. Say let n be the number of squares which lies inside the region. And let m be the squares which lies inside as well as in boundary. So then what is the area of squares which are lies inside the region? There are n squares. Say a square is of length yes, then it is n into s square. What is the area of the square which lies inside as well as on boundary? It will be m into s square. So there are so the area with this square, a small square is the area of say this region is A region, then area of A is less than or equal to m into s square, and it is greater than or equal to n into s square. By smaller and smaller square, we will get at the exact area of this square. This concept helps Archimedes in finding the area of a circle and pi value. Okay. Before going to Archimedes' approach, let's see what is the area. Corners approach to find the pi value or nothing but its area and perimeter. Okay, so consider a circle. Okay. Now divide into equal segment and arrange as in the figure. Arrange as follows. Okay, slide. Now, say this circle is C. Okay, now again. Okay, wait a second. Again, divide into equal segment as you done before. Okay, you have circles, you have squares, you have smaller squares with side yes. Now say this is a circle with this radius r. So with respect to this radius, we are writing it as s into r. Now with respect to this radius, we are writing this side as s into r. Now with respect to this notation, what is the area of this circle? That is area of C. Here C is nothing but circle, is nothing but say there are m squares which are inside the disk or inside this circle and on the boundary of the circle. Say then that is nothing but m into, now what is the area of this square? Its side is s into r, so s is s into r whole square, that is s square r square, which is greater than or equal to, say there are n number of squares inside this circle, so it is n into area of a square, that is s into r whole square, that is s square r square. Now area of C. Now what area of C? That is nothing but area of circle. Area of circle. Now here I considered a circle with radius r. Circle with radius r. Therefore, this is nothing but n into s square r square, which is nothing but area of circle with radius r, it's less than or equal to m into s square r square, r square, then that is n into s square r square, which is nothing but, if I consider a unit radius, then this will be r square into area of unit circle. Unit circle means circle with the radius 1 unit, m into s square r square. Okay, now observe this figure. Here this length is r, and what is this two length? This two length will give the perimeter, of the circle, so then this length will be half into perimeter of perimeter of circle. Therefore see this, I will name this region as D. This region as name. Therefore area of D is nearly equal to half r into 1 by 2 into perimeter of circle with radius r, okay. Now this is nothing but area of D is nothing but area of C. Therefore this is nothing but area of circle with radius r, or it is nearly equal, again it is near, or it is nothing but r square into area of unit circle. So by increasing the number of partition, we are getting it as area of circle with the radius r. Now using these two, we are getting area of perimeter of circle with radius r is nothing but it is r square into area of unit circle, divided by 2r square divided by r, so it is nothing but 2r. Now say area of unit circle, we'll take it as area of unit circle as pi, a constant. You already know it. I'm taking it as a pi and I'm naming it as a constant. It's just a constant. Area of a unit circle it is always constant. It is one number, then is pi. So we are getting it as perimeter of a circle is pi, 2 pi r. So the thing is, if using the concept of area, we got the perimeter, and moreover we got the pi value. That is, if you take any circle, then its perimeter, then its perimeter divided by its diameter is always constant. It's always constant, and that constant is nothing but pi. Constant is nothing but pi. Okay, so moving further, Archimedes approaches is just divided as above, and it took it as rectangles. Then you find the area of this rectangles and increased the number of points, and then he will get the area approaching to the area of the circle. Now, how to find the area of a curve? So this curve is mainly okay. Let's see. So there's a curve. Say this is x-axis and this is y-axis. Okay, this is A and this is A and this is B. Now divide into this AB into equal segments. Say h is equal to B minus A divided by n. Then there will be A plus h, A plus 2h, and so on. Now h, so on. Now draw lower rectangles like from f of A. That's draw rectangles as shown in this figure. Then find the area of these rectangles. Now, if you observe, the area of the first rectangle is that is f of A into this difference is now h. Now area of the second rectangle is f of A plus h into h. Now if I add all the area of these rectangles, it is f of A plus n minus 1 into h. Now I'm getting area under this. I'm not getting the exact area under the curve. I'm getting area of these rectangles under this curve. Will be noted by summation f of A plus k into h, where k is varying from 0 to n minus 1. By increasing this n, that means if I considering more and more partition of this closed interval AB, we will get as limit n tend to infinity k equal to 0 to n minus 1 f of A plus kh into h, as increasing the number of intervals, that is as tending n to infinity, we are getting area under the curve, and thus it is denoted by integration a to b f of x dx. Okay, so observe, we have considered f of x as a non-negative function, continuous function. Okay, now so another the next observation is the same curve. Consider the same curve. Okay, wait a second. Another approach. Wait a second. So this is x-axis and this is y-axis, and this is the curve y is equal to f of x. So this is A, this is b. Now again h is equal to b minus a divided by n. Then this is a plus h, a plus 2h, and so on. Then draw rectangles. Now draw rectangles. You will now using this rectangles. See now. Okay, sorry, small correction again. Okay, small correction. The previous we considered the height using f of a plus h, but in this case now find height as the lowest value in between a and a plus h. Say it as m1 as okay, yeah, m1, take it as n1 as the smallest value between a and a plus h. Then say it will be here in this figure. So then the area of this rectangle will be n1 into h. Okay, let's write here. It's n1 into h. Now area of, but now consider the smallest value in this rectangle, in this interval a plus h to a plus 2h, and name it as n1. Height will be then n1, n2, n2, and this area will be n2 into h. Similarly, find for all, you will get it is n1, n2, so on up to n minus 1 into h. Now this area, then this will be the area under this area under the curve, area of the rectangles under this curve, and this is always less than or equal to area of this curve, that is nothing but integration a to b f of x dx. Now if I consider the maximum value between a and a plus h, then and draw the rectangles and denote this maximum value by m1, then area of this rectangle will be m1 into h plus a. Similarly, for the second interval, it is m2 into h plus, and add all the areas of rectangle. You will get rectangles about rectangles, not only below, in by including the curve and some more extra space. So it will be always greater than or equal to actual area of the curve. Now see, since there is there are since this curve is bound between the interval a and b, it has some infimum and supremum. So say n is the smallest value taken by f, and m is the largest value taken by f. Then this n is less than or equal to n1, n2. So this n, so if I replace it by n, that is nothing but it is greater than or equal to n into h plus n into h plus n into h. I will get n into b minus a. This will be less than or equal to integration a to b f of x dx, which is less than or equal to, similarly this one is less than or equal to m, this one is less than or equal to m, similarly this one is less than or equal to, because this is the largest value taken by f, but here it is this mi's are the between one smaller interval, it's in large interval. So again this one will be less than into m into b minus a. So my integral, that is the area, is bounded by two numbers, n into b minus a and m into b minus a. Now let's find out what is, evaluate the integral integration of t square dt between the limits 0 and 1, between the limits 0 and 1. You can now, since you have already known what is integration and you have learned the integration in your lower classes, you can easily find this is nothing but t cube by 3, 0 to 1, hence it is 1 by 3, 1 by 3. But Cauchy's, the famous mathematician, like our Cauchy's and Euler's, they struggled so many days to find what is the area under the curve t square between the limits 0 and 1. It is not so easy in and around 1600 to 1700. So let's see how they find the area under the curve t square between the limits 0 and 1. Nothing but this integration. How to evaluate this integration? Let's consider this. Say this is x is equal to 0, this is x is equal to 1. Okay, it's not like a straight line, it's a little bit. Okay, somewhat like this. Okay. Now this is 1 now. So they divided this 0 to 1 into n equal segments such that it is 1 by n, it is 2 by n, and so on. Somewhere I will get r by n and r plus 1 by n, and draw rectangles with respect to this r by n and r plus 1 by n, and draw smaller rectangle with respect to the smallest value in between r by n and r plus 1 by n, and also draw the largest rectangle with respect for the largest value in between function value in between r by n and r plus 1 by n. Okay, now it's clear from the figure that it takes the smallest value at r by n and largest value at r plus 1 by n. In this interval, I am considering only in this. I am not considering in the entire 0 and 1. Okay, now what is the area? What is the area of this curve t square between r by n and r plus 1 by n? It is nothing but integration t square dt from r by n to r plus 1 by n. R plus 1 by n. Now, if you observe this smaller rectangle, what is the area? Its area is nothing but function value is r by n whole square into what is the distance? That is 1 by n. So it is 1 by n into r by n whole square. So this is less than or equal to the actual area, and this area is also less than or equal to the larger rectangle. What is the larger height of the larger rectangle? It is with respect to the largest value, that is r plus function value at r plus 1 by n. That is nothing but, so it is 1 by n into r plus 1 by n whole square. Now, if I find similarly, if I find all the if I find the area in each of this interval, and if I add, I will get summation 1 by n r by n whole square, where r is from 0 to n minus 1, which is less than or equal to integration. Now if I add all this integration, I am getting it is integration from 0 to 1 t square dt, which is less than or equal to summation r is equal to 0 to n minus 1 by n into r plus 1 by n whole square. Now by rearrange this is nothing but 1 by n cube into 1 square. It's nothing but start from 0 square, 1 square, 2 square, and so on up to n minus 1 square is less than or equal to integration 0 to 1 t square dt, which is less than or equal to, now again it is 1 by n cube into 1 square, 2 square, so on up to n square. n square. Now you have the result. You have the result. 1 square, 2 square plus so on to n square is nothing but 1 by 6 into n plus 1 into 2n plus 1. So using this, you will get it is nothing but 1 by n cube into, now it is n minus 1 into n into 2n minus 1 less than or equal to integration 0 to 1 t square dt, which is less than or equal to 1 by n cube into 1 by 6. Okay, here it is 1 by 6 into n into n plus 1 into 2n plus 1. Now if I take n outside, and if I can cancel with this, I will get it is 1 by 6 into 1 minus 1 by n and 2 minus 1 by n less than or equal to 0 to 1 t square dt, which is less than or equal to 1 by 6 1 plus 1 by n 2 plus 1 by n. Now as increasing the number of intervals, that is as n tend to infinity, I will get 1 by 6 into 2, that is this will tend to 1, this will tend to 2, which is less than or equal to 0 to 1 integration 0 to 1 t square dt, which is less than or equal to 1 by 6 into this will be 1 into 2 again. So this will be 1 by 3 and this is nothing but 1 by 3. So thus area is lies between greater than equal to 1 by 3, less than or equal to 1 by 3. Therefore, integration 0 to 1 t square dt is nothing but 1 by 3. Yes. Now if I give you an integration, if I give you a question to integrate, say evaluate integration minus 1 to 1 square root of 1 minus x square dx. How to find this integration? Okay, now observe the function is y is equal to square root of 1 minus x square. Since it's a function, I will take only one of the values, say this is greater than or equal to 0 square root function. So it's greater than or equal to 0. Now this implies x square by rearranging x square plus y square is equal to 1. And what it is? It is nothing but circle, and y is greater than or equal to 0. So it will represent only the upper half of the circle, like circle. It's a unit circle. So this integration, it represents the area of the circle, half of the circle. Half area of the circle, half into area of the circle. And what is this? It is nothing but 1 by 2 into, what's the area of this full circle, unit circle? It is pi. It is area of this circle is pi, but I need only half, so it is pi by 2. So integration is this. So in mathematics, visualizing the things are very important. You should visualize things. So then okay, I'm not going to further more in deep in this. Okay, now you understood how the integrations are introduced. But see, observe here I am considered only the bounded continuous function in over non-negative functions. So there's not much difficulty in if I consider a fully non-negative function, negative function. Just by multiplying minus, you will get a non-negative function. Okay, but I'm not observing any functions of form like this. Say functions like this. Okay, so and now consider the function 0, 1, 2. So it's 1, 2. So this is the function which is not taking any value at 1. That is f of x is equal to 1 if x 0 less than or equal to x less than 1, and it is 2 if 1 less than x less than or equal to 2, and this you can observe x is not taking any value at 1, so it has a discontinuity at 1. Now if I ask you what's the area under the curve, you can just observe, yeah, this is area of this and area, this is the area of this. By adding these two areas, I'm getting area under the curve. But what about this point? Why we should neglect that point? Because the point, the function value at 1 is not defined. So will it affect the area? Will it affect the area? It's the question. How and why? Why this is the area? Why this will not affect the area? And this was developed by Riemann. This was developed by Riemann. This was developed by Riemann. Okay, then so one of the interesting fact is, wait a second. So it's RIE, okay, RIE, Riemann integration. So this was developed by Riemann, the mathematician Riemann. When he was writing the research thesis of this research, his research title was, what is the meaning of integration a to b f of x dx? It's his research thesis title is, what is the meaning of this? And when he was finding this, when he was writing this research thesis, his guide is Dirichlet. He is also one of the famous mathematician. You will come to know about him in the next incoming classes. Dirichlet, he said, he asked, what is the integration of f of x is equal to 1 if x belongs to Q and 0 if x does not belongs to Q, in between 0 and 1. That he asked it about a function which is take 1 at rationals, 0 at irrationals. Find between 0 and 1. Find the area between 0 and 1. But his idea is failed here. His idea is Riemann's integration fails to identify the area of this curve between 0 and 1. Therefore, the integration technique is not stopped here. It is continued further in 1902. Mathematician Henry Lebesgue introduced a new concept. It is measure theory, which you will study in detail in the next semester, the third semester. So we are going to study Riemann integration in next class, from the next class. Okay, thank you.